Something is happening 13 billion light years away, and the people who are supposed to be telling you about it are choosing their words very, very carefully. The James Webb Space Telescope has now captured data so contradictory, so structurally impossible under every model humanity has ever built, that the scientists analyzing it are not celebrating. They are arguing, quietly, behind closed doors, in peer-reviewed papers written in the language of caution. But the data doesn't speak cautiously. The data speaks in language of impossibility. And today, we are going to decode exactly what that means for everything you thought you knew. There is a question that nobody in mainstream science is asking loudly enough, and it goes something like this. What happens when the most powerful telescope ever constructed by human civilization points itself at the oldest corners of the universe and comes back with data that should not exist? Not data that is surprising, not data that is unexpected, data that is, according to every model, every equation, every cosmological framework that took generations of the brightest minds on Earth to construct, fundamentally impossible. That is the situation we are in right now, and the fact that most people are still talking about James Webb as though it is simply a prettier version of Hubble tells you everything about how poorly this story is being communicated to the world. Let us start with what the James Webb Space Telescope actually is, because the scale of this machine is not something the human brain is naturally equipped to grasp. Its primary mirror stretches 6.5 meters across, composed of 18 gold-coated beryllium hexagonal segments working in perfect synchronized harmony. It collects more than 6 times the light that Hubble ever could. It does not observe invisible light. It sees the universe in infrared, which means it can pierce through clouds of cosmic dust that would stop any other telescope cold. And it sits nearly 1.5 million kilometers from Earth, at a gravitational sweet spot called the L2 Lagrange point, where it can remain stable and cold enough to function at the limits of what physics allows. Now, this was not built to take pretty pictures. This was built to answer the oldest question humanity has ever asked. Where did all of this come from? The telescope launched on December 25th, 2021, and began full science operations in mid-2022. By 2026, it has completed nearly 4 years of observations, and its cumulative impact on astronomy is extraordinary. Every month brings new results challenging established models of galaxy formation, atmospheric chemistry on worlds orbiting other stars, and the physical processes sculpting nebulae and star clusters. But here is where it gets interesting, because the word challenging does not capture what is actually happening. The word you need is dismantling. Webb is not refining our understanding of the early universe. It is pulling the foundations out from underneath it, one impossible image at a time. Think about what the standard model of cosmology told us. The Big Bang happened approximately 13.8 billion years ago. In the first few hundred million years, the universe was a hot, dense plasma of hydrogen and helium, slowly cooling, slowly condensing under gravity. Stars formed, those stars exploded. Their remnants seeded new stars with heavier elements. Galaxies accumulated over billions of years, slowly building structure, slowly gaining mass, slowly developing the complex chemical signatures that define a mature astronomical system. That was the story. That was the settled science. And then Webb looked at the early universe and found something that made that story collapse. Almost as soon as the telescope was switched on, astronomers saw something surprising. There seemed to be big, bright galaxies everywhere in the early universe. They had predictions about how many galaxies they should see and how large those galaxies would be, but there were far more of them than they had imagined. This led to a flurry of headlines and a whole lot of head-scratching in the field because, at first glance, the galaxies the astronomers were seeing seemed to be impossible. There simply wasn't enough time since the Big Bang for that many stars to have formed according to the standard model of cosmology. Read that again. Not a few rogue data points, not anomalies that could be explained away with calibration errors. A systematic, consistent, overwhelming pattern of galaxies that should not exist, filling the early universe in numbers and with structural complexity that the standard model says was impossible. In mid-2025, Webb identified a galaxy designated JWST Z+0 at a redshift of 14.32, placing it approximately 290 million years after the Big Bang. At that point in cosmic history, there simply hasn't been enough time under standard models for gas to collapse, form stars, build heavy elements through stellar fusion, and assemble those elements into a structured galaxy with visible spiral features. And this is where everything changes. Because this is not a single outlier. This galaxy is one data point in a growing, terrifying trend. Webb keeps finding them, over and over, galaxy after galaxy, at distances and ages that should be cosmologically sterile, cosmologically empty, cosmologically too young to harbor the kind of complexity being detected. And the scientific community, to its credit, is not pretending this away. The James Webb Space Telescope's view of the infant universe has delivered genuine surprises: bright galaxies, rapid star formation, and evidence of accreting black holes only a few 100 million years after the Big Bang. These findings have ignited debates about whether our best cosmological theories can survive new data, let that sink, in. Not whether they need adjustment, whether they can survive. That is the scale of the crisis unfolding in the world of astrophysics right now, and it is happening in real time, in published papers, in conference rooms, and in the data streaming back from a machine floating silently 1.55 million kilometers away from us. But here is where it gets worse, because if the impossible galaxies were the only problem, scientists might be able to contain the damage, adjust the efficiency parameters in star formation models, tweak the dark matter interactions, introduce a new variable here or there and keep the framework intact. That is the usual mechanism of scientific progress. You find an anomaly, you expand the model, you move forward, but Webb is not giving them that option. Because alongside the impossible galaxies came something that no adjustment to galaxy formation models can explain away: the black holes. JWST has found supermassive black holes existing just 500 to 700 million years after the Big Bang that are far too massive to have grown from stellar mass seeds through normal accretion. This suggests either direct collapse black holes formed from primordial gas clouds, or our understanding of black hole growth is fundamentally incomplete. Think about what that means. A supermassive black hole, the kind that sits at the center of galaxies and contains the mass of hundreds of millions of suns, is supposed to grow slowly. It starts as a stellar remnant, the collapsed core of a dead star, perhaps a few times the mass of our sun. And then over billions of years it feeds. It pulls in surrounding gas and dust and matter, slowly accumulating, slowly growing, in a process called accretion that takes cosmic time to produce cosmic results. That is the model. That is what the textbooks say. And Webb found black holes so massive, so early in cosmic history, that they could not possibly have grown through that process. Not even close. Researchers took a long look at a little red dot from about 750 million years after the Big Bang that is gravitationally lensed by a cluster of galaxies in the foreground. They concluded that the object is a naked supermassive black hole, an estimated 50 million times the mass of the Sun, without any discernible stars surrounding it. If that mass estimate is correct, the implication is that the black hole OR may have formed as a large seed, possibly via direct collapse before any galaxy was present. A naked supermassive black hole. No galaxy around it, just pure concentrated gravitational mass hanging in the infant universe, billions of years before it should have been able to exist. This is not a refinement to the standard model. This is a frontal assault on the entire sequence of how we believed the universe organized itself. And the implications do not stop there. Because according to informed sources within the astrophysics community, the real story is not just about whether the models need updating. The real story is about what we get wrong when we discover our foundational assumptions were incorrect. Cosmology is not just an academic exercise. It is the framework through which we understand time, space, causality, and ultimately our place in a universe we thought we were beginning to comprehend. When Webb reveals that supermassive black holes existed before the galaxies that supposedly birthed them, it is not correcting a footnote. It is questioning the chapter headings. Since its launch in late 2021, the James Webb Space Telescope has been glimpsing some of the earliest epochs of cosmic time. Its observations have stretched cosmologists' timelines of when galaxies may have first started to form. And now some of the telescope's farthest observations yet have revealed sources of blue ultraviolet light from an epoch when stars shouldn't have existed yet. The observations indicate 9 new light sources, with 6 at redshift 17 and 3 at redshift 25, when the universe was only 200 million to 100 million years old. 200 million years after the Big Bang. 100 million years after the Big Bang. There is light where there should be nothing but darkness. There is structure where there should be only chaos. And the deeper Webb looks, the more it finds. But the crisis in cosmology is only the first layer of what this telescope is uncovering. Because while one team of astronomers is rewriting the history of the universe, another team is doing something far more immediately personal. They are looking at planets around other stars. And what they are finding is something that the scientific community is being extraordinarily careful about, because the implications, if confirmed, would represent the single most consequential discovery in the history of human civilization. The planet is called K2-18b. It orbits a red dwarf star approximately 124 light-years away from Earth, which sounds like an enormous distance until you frame it the right way. In a galaxy that is 100,000 light-years across, containing over 200 billion stars, 124 light-years is your next-door neighbor. This is practically local. And what Webb found in the atmosphere of this world has generated more scientific controversy, more heated debate, and more careful, deliberate language than almost any discovery in recent memory. A team of astronomers detected what they call the most promising signs to date of a possible biosignature, or signs of past or present life linked to biological activity, on an exoplanet named K2-18b. Using the James Webb Space Telescope, the team detected chemical fingerprints within the atmosphere of K2-18b that suggest the presence of dimethyl sulfide, or DMS, and potentially dimethyl disulfide, or DMDS. On Earth, both molecules are only produced by microbial life, typically marine phytoplankton. Let that sentence land fully before moving forward. On Earth, those molecules are only produced by life, by living organisms, by biology. And Webb found their chemical fingerprint in the atmosphere of a world 124 light-years away. The team found a possible biosignature, the potential fingerprint of life, within its atmosphere, although they say they're remaining cautious and that this isn't a confirmed detection. The chemicals detected are the same as those produced by marine-dwelling organisms on Earth. Marine-dwelling organisms, ocean life, the kind of microscopic single-celled organisms that float in Earth's seas and produce these specific sulfur-based compounds as biological byproducts. And the planet where this signal was detected is theorized to be a Hycean world, meaning a world with a deep global ocean beneath a hydrogen-rich atmosphere, the very type of environment where such organisms might plausibly exist. This is not coincidence. This is the universe leaving fingerprints. The new data comes from JWST's mid-infrared spectrograph and brings the detection up to a 3 sigma level, meaning there is a 0.3% probability the signal appeared by chance, a 0.3% chance this is noise, a 99.7% chance that something real is producing the signal. Now, in particle physics, the gold standard for a confirmed discovery is 5 sigma, which corresponds to a probability of roughly 1 in 3.5 million. But in the history of astronomy, 3 sigma detections have launched careers, funded missions, and reshaped fields. And this 3 sigma signal is not standing alone. It came from a completely different instrument, a different wavelength range, with no overlap to the previous observations that first hinted at the same molecules. That is what makes it so difficult to dismiss. 2 independent lines of evidence using different tools, pointing at the same chemical signature on the same world. What most people are not seeing is the structural significance of how this detection was made. The team used a method called transmission spectroscopy, where they measured the starlight filtering through K2-18b's atmosphere as the planet passed in front of its star. Different molecules absorb different wavelengths of light in precisely predictable ways, leaving chemical with fingerprints in the spectrum like a cosmic barcode. Webb reads those barcodes with a precision that no instrument in history could match. And when it read the barcode of K2-18b's atmosphere, it kept finding the same molecular fingerprints in 2 independent observations with 2 different instruments across different wavelength ranges. This is an independent line of evidence, using a different instrument than we did before and a different wavelength range of light, where there is no overlap with the previous observations. 2 independent detections, same molecule, same world. The same chemical that marine microbes produce in Earth's oceans, floating in the sky of a planet 124 light-years away. And here's the part that deserves genuine, sustained attention. The scientific debate that followed was not about whether the detection was politically inconvenient or philosophically uncomfortable. It was about whether it was statistically ironclad. That is healthy science working correctly. But what it tells us is that the signal is real enough to argue about, specific enough to dissect, and persistent enough that it has not simply evaporated under scrutiny. Of course, the full picture requires the honesty of uncertainty. Independent teams, reanalyzing the same observations, have not found the evidence robust. In some reductions, the signal weakens or disappears, and in others, ordinary molecules fit the data about as well. A group led by Luke Wellbanks showed that the apparent dimethyl sulfide signal could be swapped for ethylene, an unremarkable hydrocarbon with no loss of fit. This is the nature of frontier science. The same data, processed differently, tells different stories. And that is not a scandal. That is the cutting edge. That is what it looks like when humanity is genuinely at the boundary of its knowledge, peering into territory where certainty has not yet arrived and may not arrive for years. But consider the geometry of the situation. We are not talking about a signal that has been definitively ruled out. We are talking about a signal that persists under many analyses, weakens under others, and has not been eliminated. We are talking about a planet in the habitable zone of its star, theorized to host a global ocean where 2 different Webb instruments, observing at different wavelengths, have both returned data compatible with the molecular fingerprint of ocean life. At some point, the weight of coincidence becomes too heavy to carry as coincidence. Now, step back for a moment and take in the full scope of what is happening here. because we have not even touched the other discoveries Webb has made in the past year that are independently reshaping our understanding of what the universe is and what it contains. A giant planet had been hiding inside one of astronomy's most closely studied planetary systems, concealed by a bright disk of cosmic dust. Webb revealed Beta Pictoris d through atmospheric traces of carbon monoxide, water vapor, and methane. A planet was hidden in one of the most studied systems in all of astronomy, invisible to every instrument that came before Webb, only revealed when this telescope's infrared eyes cut through the dust. What else are we missing? What other worlds are hiding behind veils of cosmic material that only this machine can pierce? Scientists discovered a planet where rock clouds vanish every night. Not water clouds, not ice clouds, rock clouds, silicate particles, the stuff that makes planetary crusts, vaporizing during the day and condensing into liquid rock droplets at night, forming clouds that dissolve with the dawn. This is not science fiction. This is data collected in 2026 by a telescope orbiting a gravitational equilibrium point between Earth and the Sun, transmitting observations of worlds so alien that the human imagination, even at its most creative, could not have engineered them without the evidence to guide it. Astronomers have uncovered surprising evidence of a thick atmosphere surrounding TOI 561b, a scorching, fast-orbiting rocky planet once thought too extreme to hold onto any gas. A world thought to be atmospherically barren, stripped clean by its star's radiation, has been found wearing a thick atmospheric coat that should not exist. And this matters not just as a curiosity, but as a data point in a larger pattern. Webb keeps finding atmospheres where none should exist, molecules where none should be present, structure where none should have had time to form. The universe, it appears, is far more creative, far more efficient, and far more structurally complex than our best models ever predicted. Astronomers discovered a rare, tightly packed collision of galaxies in the early universe, suggesting that galaxies were interacting and shaping their surroundings far earlier than scientists had predicted. Researchers identified an ongoing merger event of at least 5 galaxies about 800 million years after the Big Bang, along with evidence that the collision was redistributing heavy elements beyond the boundaries of the galaxies themselves. 5 galaxies colliding and merging 800 million years after the Big Bang in a universe that was supposed to be too young, too sparse, too cosmologically immature for such a complex interaction. And the surrounding gas was already seeded with heavy elements, the kind of elements that only form inside stars that have lived and died, which means there must have been generations of stars before this collision that nobody's model predicted should have existed. This is the chain of evidence. Each discovery is not isolated. Each impossible finding connects to the others. The impossible galaxies mean star formation was faster than expected. Faster star formation means more stellar deaths, more heavy elements seeded into the universe earlier. More heavy elements earlier means more complex chemistry earlier. More complex chemistry earlier means the building blocks of planets, atmospheres, and potentially life were available billions of years sooner than the standard timeline allows. The implications cascade. And at the far end of that cascade is K2 to 18b, a world 124 light years away, with molecules in its sky that organisms produce in Earth's oceans, orbiting a star in a universe that turns out to have been preparing the conditions for biological chemistry far earlier than we imagined. Astronomers using the James Webb Space Telescope have uncovered an extraordinary concentration of small organic molecules deep inside the heavily concealed core of a nearby galaxy. Organic molecules, the chemical precursors to biology, concentrated in the heart of a galaxy, shielded from observation by dust so thick that only Webb's infrared vision can penetrate it. Life's ingredients are not rare. They are not confined to special conditions near Earth-like stars. They are everywhere. They are inside. Galaxies, around forming stars, frozen into ice in neighboring star systems. Astronomers using the James Webb Space Telescope have uncovered a trove of complex organic molecules frozen in ice around a young star in a neighboring galaxy, including the first ever detection of their kind in that environment. The first ever detection. In a neighboring galaxy, in ice around a young star. The ingredients are being delivered to new worlds before those worlds have even finished forming. And then there is 3I Atlas. In 2025, the third interstellar object ever detected, Comet 3I Atlas, was discovered passing through our solar system. JWST turned its powerful instruments on this visitor from another star system, analyzing its composition to learn about the conditions in its home system. A comet that did not form here, a traveler from another stellar system passing through our cosmic neighborhood. And Webb examined its chemistry to understand what the universe looks like in places we cannot visit. An interstellar envoy, carrying the chemical signature of a world we will never see, close enough for Webb to read its composition like a message in a bottle thrown across the stars. What most people are not seeing is that this is not a series of disconnected scientific achievements. This is a coherent shift in humanity's understanding of its place in the cosmos. Every discovery connects. The impossible galaxies prove the early universe was more productive than we thought. The direct collapsed black holes prove the formation of cosmic structure happened through mechanisms we did not know existed. The organic molecules everywhere prove that the chemistry of life is not a planetary accident, but a universal tendency. And K2-18b, floating quietly, 124 light-years away with its tentative, maddening, persistent chemical signal, sits at the center of a web of evidence that the universe has been doing this for longer, in more places and in more ways than human science, before this telescope was remotely equipped to perceive. The numbers that frame this story deserve the dramatic weight they carry. Webb operates at a temperature of minus 233 degrees Celsius, cold enough to detect the faint infrared glow of objects billions of light-years away without its own heat contaminating the signal. It transmits roughly 57 gigabytes of compressed scientific data per day back to Earth. Its observations have already produced thousands of peer-reviewed scientific papers. And it was designed to operate for 10 years, though current fuel estimates suggest it may function for 20. Which means whatever it has already found may represent less than a quarter of what it will eventually reveal. Webb confirmed the earliest supernova to date. This dying star exploded when the universe was only 730 million years old. Webb's sharp infrared capability also allowed astronomers to locate the supernova's very faint and distant host galaxy, the earliest stellar death ever confirmed, a star that lived and died when the universe was barely beginning, leaving behind the heavier elements that would seed future generations of stars, planets, and potentially life. Every explosion like this one in the early universe scattered the ingredients further, and Webb can now see those explosions, read their light, measure their chemistry, and trace the threads of cosmic recycling across 13 billion years of history. This is not chaos. This is strategy. The strategy of a universe that operates on timescales and at scales of complexity that dwarf anything the human mind evolved to comprehend. And the James Webb Space Telescope is the first instrument we have ever built that is powerful enough to watch that strategy unfold in real time across cosmic history with enough resolution to see not just that things happened, but how they happened and what they produced. The question that science is now sitting with is one that does not have a comfortable answer. If galaxies formed faster than expected, if black holes grew by mechanisms we did not know were possible, if organic chemistry is universal rather than exceptional, if the ingredients of life have been seeding every corner of the cosmos for billions of years longer than we imagined, then the probability equation for life itself needs to be completely recalculated. And if it needs to be recalculated, then so does everything downstream of that equation. The assumptions we made about how rare life is, the assumptions we made about how special Earth is, the assumptions we made about whether we are alone. These are not philosophical questions. These are now empirical questions. And James Webb is the instrument that turned them empirical. Every observation it returns narrows the range of possibilities, tightens the constraints, and forces the field to confront evidence rather than theory. And the evidence in 2026 is pointing in a direction that the most cautious, the most rigorous, the most skeptical scientists in the world are now compelled to take seriously. The K2-18b data will be revisited. More observation time will be allocated. Better analysis pipelines will be developed. The signal will either strengthen or dissolve. And if it strengthens, the announcement that follows will be the most important scientific statement in human history. If it dissolves, it will tell us something almost equally important, that the chemistry of life is so ubiquitous in the universe that ordinary non-biological processes can mimic its signatures in the atmospheres of distant worlds. Either answer changes everything, and Webb will keep looking. It will keep pointing its gold-coated mirror at the oldest light in the universe, at the atmospheres of worlds around other stars, at the dense cores of nearby galaxies, at interstellar visitors passing through our cosmic neighborhood, at the dust-shrouded nurseries where new stars are forming right now. Each pointing returns data. Each data set produces papers. Each paper shifts the field. And somewhere in the next year, or the year after that, or the year after that, something will come back from that telescope that will not be deniable, will not be tentative, will not require the careful language of scientific caution. Something will come back that is definitive. The question is not whether James Webb will make a discovery that rewrites everything. Based on what it has already found, the question is which discovery it will be, and whether the world will be ready for the answer. The impossible galaxies suggest the universe is older in its complexity than we knew. The impossible black holes suggest structure formed through mechanisms we are only beginning to understand. The organic molecules everywhere suggest chemistry is conspiring toward complexity at every scale. In one world, 124 light years away, is holding a signal in its sky that either confirms we are not alone or reveals that the universe is so chemically rich that it mimics the fingerprints of life without even trying. Both possibilities are extraordinary. Both possibilities are, in their own way, terrifying. And right now, floating silently at the edge of Earth's gravitational embrace, a machine made of gold and beryllium and human ingenuity is staring into the dark, collecting photons that traveled for billions of years to reach its mirror, and translating them into data that we are only beginning to understand how to read. The universe has been speaking for 13.8 billion years. We have only just built the instrument capable of listening. And what it is saying, in the language of light and chemistry and gravity and time, is that everything we thought we knew was only the beginning of the question. What is coming next from Webb? What signal is already embedded in its data, waiting for the right analysis pipeline, the right wavelength, the right comparison to reveal itself? What is already in the archive that nobody has yet recognized for what it is? The impossible galaxies were hiding in the data before anyone named them impossible. The black holes that shouldn't exist were there before anyone measured their mass against the age of the universe and realized the timeline didn't add up. And somewhere in 57 gigabytes of data, arriving every day from a machine that never sleeps, never blinks, never looks away from the sky, the next impossible thing is already waiting. The universe is not done being strange. Webb is not done looking. And the story of what this telescope has captured and what it will capture next is not a story that ends. It is a story that is only now, after 13.8 billion years of silence, beginning to be told.